Hello, welcome back. Today we're going over section 8.8 on improper integrals. So if you recall, way back when you first learned about the fundamental theorem, we had the definition that the integral from a to b of f of x dx had to be continuous on ab. With an improper integral, either a or b are infinity, negative infinity. So basically we can approach but can't reach them. So we have an improper integral when that happens. We can still use limits to deal with that, though. So we can say if we have the integral from, say, a to infinity of f of x dx, and we would still like to find that area, we can simply say we'll take the limit as b approaches infinity of integral from a to b f of x dx. You can do a similar one for a if we're going from negative infinity to b. Take the limit as a approaches negative infinity. So you can write similar definitions if you have a negative infinity. If you have both, you simply split the interval. That's worth showing you we have both. So this would be the integral from negative infinity to some point c, and we'll do that limit as c goes to infinity. Plus integral c to infinity f of x times dx. So basically we just find somewhere to split it and do our limits individually. So c here is at some point, I apologize, we can just get rid of the limit there. We do need to include f of x dx, however. So we basically just split it. One from negative infinity to c and use the limit on the next step. One from c to infinity, use the limit on the next step. If the limit exists, the function converges, else it diverges. So we'll start with integral from 1 to infinity of 5 over x times dx. So notice here we're approaching positive infinity, so an improper limit, but we have the limit as, we'll say we let b go to infinity here. Antiderivative of 5 over x would be 5 natural log of x, and we're evaluating from 1 to b. So then this is 5 natural log b minus 5 natural log 1. And we're, of course, still letting b approach infinity. So 5 natural log of 1 drops off. So this is then the limit as b approaches infinity of 5 natural log of b. Natural log of 1 is 0. Anything times 0 is 0. This will still diverge. This is still approaching infinity. So this would have an infinite area. Our next one does not have an infinite area, however. If we go with the integral from 4 to infinity of e to the negative 7x times dx. So we'll take the limit as b approaches infinity. So here's our a, here's our b. B is going to infinity. We take the integral of e to the negative 7x, so negative 1/7 e to the negative 7x, and evaluate from 4 to b. So then this is the limit as b goes to infinity. We have negative 1 over 7e to the 7b minus negative 1 over 7e to the negative 28, positive 28 if we drop it downstairs. Just drop it downstairs into the denominator. So looking at what happens to these guys, as b goes to infinity, the numerator is constant, the denominator blows up, gets bigger and bigger without bounds. This term drops to 0. Minus a negative 1 turns into 1, so this would be 1 over 7e to the 28th. So it is a finite area. All right, next one we get to play with a little trig substitution. Integral from 0 to infinity of 6 over x squared plus 1 times dx. Remember, when we're u squared plus a squared, you're using x as tangent, a tangent theta. So integral from 0 to infinity, we'll pull that 6 out, 1 dx over x squared plus 1. And then our let line, let x equal 1 tangent theta, or simply tangent theta, since 1 squared is still just worth 1. So then dx is secant squared theta times d theta. So we have 6 integral from, I'll just put in arbitrary a to b, and we'll translate it back when we get back to x from theta. So dx is secant squared theta, d theta. Downstairs, x squared is tangent squared. And we still have our plus 1. Hopefully you recall, secant squared minus tangent squared is worth 1. That one should be as familiar to you at this point as sine squared plus cosine squared is 1. If it's not, just keep working on it. So tangent squared plus 1 is secant squared. So we have 6 integral a to b secant squared theta over secant squared theta d theta. So 6 integral from a to b of d theta. So that is 6 theta from a to b. Now let's get rid of our theta. So theta is, as you can see from our original, theta would be arctan x. And we're evaluating instead of just the generic a to b. Now we're looking at 0 to infinity. So this is the limit as b goes to infinity of 6 arctangent b minus 6 arctangent 0. So if our arctangent is infinity, it implies that the cosine was 0. Remember, tangent is sine over cosine. If it's approaching infinity, that means cosine was 0. So if cosine is 0, that is happening at pi over 2. So 6 pi over 2 minus 6, arctangent being 0. Remember, tangent is sine over cosine, so this means that the sine was 0. That happens at 0. So this would be 3 pi for our limit. So again, when you see these arctangents, remember tangent is just sine over cosine. And think of what would make that go to 0, what would make that go to infinity. All right, occasionally we do get to play with L'Hopital's rule with these improper integrals. So we'll look at integral from -5 to infinity of x plus 5 e to the negative 2x times dx. So this one we have a little bit of L'Hopital and a little bit of, hopefully you recognize here, a little bit of integration by parts. So if we let u equal the x plus 5 and dv be the rest, e to the negative 2x times dx, then du is worth dx, v is -1/2 e to the negative 2x. So u times v, x plus 5 by -1/2 e to the negative 2x, evaluated from -5 to infinity, minus integral of v times du, -1/2 e to the negative 2x times dx. Okay, so a little bit of cleanup, making this first part a little bit prettier. So we have opposite of x plus 5 over 2e to the 2x, evaluated as before, -5 to infinity, minus a negative turns into a plus, so plus 1/2, and then do the antiderivative of e to the negative 2x, so that's -1/2 e to the negative 2x. Also evaluated from -5 to infinity. So we have opposite of x plus 5 over 2e to the 2x minus 1 over 4e to the 2x, all of that evaluated from -5 to infinity. At this point, then, we have infinity over infinity. We can use L'Hopital's rule on this one. And let's see. So let's get a common denominator going. And then we'll use our friend L'Hopital again. So let's see, our common denominator would be a 4e to the 2x. So that just means we'll hit this guy top and bottom with a 2. So we have -2x minus 10 minus 1 over 4e to the 2x, evaluated from -5 to infinity. We can call that a -2x minus 11 over 4e to the 2x, evaluated from -5 to infinity. Drawing out the infinity, we have negative infinity over infinity. L'Hopital's rule would be appropriate. So differentiating the top, we're looking at the limit as, we'll call it b. B goes to infinity, -2 over 8e to the 2x. And we'll look between -5 and infinity. So we have -1 over 4e to the infinity minus -1 over 4e to the -10. E to the infinity gives us an infinitely large denominator, constant numerator. This term will drop to 0. Minus a negative turns into a plus, so this is +1 over 4, and either e to the -10th at the bottom or e to the 10th at the top. More commonly, you'll just see it as e to the 10th over 4.